Recall the first constraint optimization problem involving the airline industry. In solving this problem, we determined that we needed to equalize the marginal revenues of the two market segments, and that would maximize sales revenues. We've repeated the point that in order to maximize in a constraint optimization problem, we need to equate marginals. So if we're maximizing profit, we equate marginal profitability. And if we are maximizing sales revenue, we equate marginal revenues. Recall that in equating the marginal revenues, we obtained two different prices, and in this case, we obtained a higher price for business passengers and a lower price for tourists. We're changing the problem slightly, and in this particular version of the problem, we're going to have a fixed price for one market segment and a negatively sloped demand for the second market segment. This problem reads as follows. In summer, American Airlines flies charters from Dallas to Disney, and it has started advertising $100 airfares for kids under 12 years of age if they are traveling in the company of an adult. In order to maximize revenues on this route, how many adults should American desire on each flight? If the demand for tickets by adults is given by Q equals 330 minus P, and there's a virtually unlimited supply of children at $100. Each flight carries a maximum of 270 passengers. So unlike the previous problem, where we had two negatively sloped demand curves, we now have one negatively sloped demand curve and a horizontal demand curve, and the capacity of our aircraft is going to be 270 passengers. We still need to apply the rule of equating marginals in order to get the optimum solution for this problem. But before we get there, let us think through the problem in a very basic way to see what errors can be made if we do not quickly apply the efficiency principles. The first thing we're going to do is to try to charge everyone $100 and see how much revenue we can make, how much profit also we can make at $100. The first thing we're going to try to do here is to see what the profitability looks like when we charge everyone $100. It is clear that with 270 seats at $100 each, we would earn $27,000 in revenue. And the cost is $20 per passenger times 270 passengers. That's $5,400 plus $32,000 in fixed costs, so that's $37,400. You can see that the profit would be a negative $10,400. Charging a price of $100 then would result in a loss. We change the problem slightly, and rather than charge a price of $100, let us charge a price of $165 to adults and $100 to children. The price of $165 represents the midpoint on the linear demand curve, and if we only had adults to carry on our flight and no children, or if children were flying for free, you could see that a price of $165 would maximize the revenue from adults, and that would maximize revenue in this problem. So at the midpoint, for Q equals 330 minus P, the price is $165, the quantity is $165, that's for adults, and the revenue is $165 times $165, which is $27,225. With 165 adults on a plane that carries 270 passengers, there's 105 empty seats. So we fill those seats with kids at $100. The revenue from kids, $10,500, plus the revenue from adults, $27,225, yields a total revenue of $37,725. $37,725. Remember, the cost is going to be $32,000 plus $5,400, $37,400. We subtract that cost from the revenue, and we are left with a profit of $325. We move from a loss of $10,000 to a profit of $325. Now let's ask the question, what happens if we raise the price above $165? Will we increase the total revenue? So we're going to raise the price by $1 from $165 to $166. And notice that that will bring in 164 passengers. 166 times 164 gives us $27,224, which is $1 shy of where we were when we charged a price of 165 to 165 passengers. So we've lost $1, but that seat that has become available can now be sold to a kid for $100. So we gave up $1 and we're going to make $100. So the net difference will be a gain of $99. So the overall revenue will go up by $99 to $37,824. The profit then would go up by $99 to $424. We now ask the question, how much higher can we push the price for adults so that we can get to the maximum level of revenue? Let's try a price of $200. We plug 200 into the demand equation and we get a quantity of 130 adults. So 200 times 130 is $26,000. 130 adults means there's 140 seats available for kids. 140 seats at $100 is 14,000. So we have 40,000. A revenue of 40,000 less a cost of 37,400. So as we raise the price for adults to $200, the profit goes up to $2,600. By the way, notice the cost for the airline will not increase because we're filling the seats at $20 per person. So the cost will remain at $37,400. So cost becomes irrelevant to the profit question. We can just go for the maximum revenue under these conditions. The optimum solution to this problem would be to push the price up to $215 for adults, leaving the price for kids at $100. And this occurs when we apply the rule for maximizing total revenue under constraining conditions, which is to equate the marginal revenues across the two market segments. Recall we've said that in a problem like this, we equate the marginals and we invoke the constraint. So the constraint is the number of passengers we can seat, and we equate the marginal revenue for adults to the marginal revenue for children, which will be $100. Notice the marginal revenue for kids is the same as the price because the demand curve is horizontal. So the demand curve and the marginal revenue curve will be coincident at every point. For the maximum revenue, we equate the marginal revenues, and since the marginal revenue for kids is $100, the marginal revenue for adults will be 330 minus 2Q, and that tells us that QA, the quantity of adults, is optimized at 115. We plug Q equals 115 into the inverse demand equation for adults, and we get a price of $215, and the revenue would be $215 times 115 adult passengers, which is $24,725. Because there are 115 adults, there will be room for 155 kids to get the total to 270. That would then bring in a revenue of $15,500 plus $34,725. And that yields a profit of $2,825. This is the maximum profit that can be had under these conditions. Notice that the price for adults is now more than double the price for kids, and all the bad intuition that one might muster goes away because one knows that the rule to follow is to equate marginal revenues, and once we do that, the prices that fall out would be a price of $100 for kids and a price of $215 for adults. Here you see the inverse demand equation for adult passengers. P equals 330 minus QA. And if we were to price at the midpoint, you recognize we earn a revenue of $27,225, and allocating the remaining 105 seats to children would yield another $10,500 for a total of $37,725, as we discussed earlier. The optimal solution here is to carry 115 adults at a price of $215. That leaves 155 empty seats, so we fill those seats with children at $100, and our revenue would be $40,225. That's the highest revenue of any variation of the problem. If one wants to set the problem up formally as a Lagrangian, we want to maximize the revenue streams, which is 100 times the quantity of kids, plus the inverse demand curve here to get the price, plus 330 QA minus QA squared, subject to QA plus QK equals 270. When we differentiate this equation, we get lambda equals 100, and we get QA equals 115, and PA equals 215. And you see the revenue is $40,225. Here's another version of the problem we just looked at. This version includes an advertising effect from the Kids Fly Free program. Instead of charging kids a price of $100, we're going to allow kids to fly free and see what impact that has on the demand by adults. So we notice the demand for adults will have the added impact from the Kids Fly Free program in that adults will be more likely to travel on this airline because of this particular program. The coefficient of 0.5 on the QK variable can be interpreted as saying that a family with 2 kids would increase their demand on this airline by 1 adult. For example, prior to the Kids Fly Free program, the demand by adults would have maximized its revenue at the midpoint of the demand curve, which is Q equals 165 and P equals 165. Now we can see this rightward shift of the demand curve would yield a higher price and a higher quantity of adults, and we have to calculate what that would be based on the fact that we have 270 seats to allocate. The question asks you to explain as fully as you can the effect of the Kids Fly Free program on the demand by adults. Part 2, what restrictions or constraints would you put in place to ensure minimum cost to your airline? And part 3, what price would you charge adults in order to maximize revenue on this flight?